Thank you very much for the introduction. Today I will be talking about modeling aggregation induced emission in molecular crystals. That is a topic we've been working on for the last few years. What do we care about aggregation induced emission? If we talk about highly emissive organic materials that are very useful for many applications, considering like OLEDs or fluorescence bioproof or organic lasers, all of these applications will require to have materials with a high emissive response. A problem that we have in the case of organic molecules is like in many cases, when you aggregate them, you form a stable pi-pi interactions or a stabilized shared transfer states. And as a result, you have quenching of emission. You activate non-radiative decay mechanisms, and the result of that is like the material is less emissive than when you are in a dilute solution. So in the last few years, there's been quite a lot of interest in looking at how to maximize emissive response in the solid state or in concentrate solution. And this phenomenon is known as aggregation induced emission. And basically what we have is like, we try to block the decay of these materials when they are in concentrate solution or solid state by restricting the vibrations that are activated for this system. So basically we have like for any non-radiative decay process, we have a vibrational and an electronic component. So we have to take into account both components when we try to improve the emissive response of the materials. So if we think about a typical potential energy surface and we think of something like that, or this is a graphical representation, we can see like we can have non-radiative decay because or either because we have overlap between the vibrational states of the systems, or because we are in a region of very small energy gaps and we reach conical intersections that is available for the system. So consider these two possible conditions. There are two models that are normally used to understand how you can improve the emissive response in the solid state. One is restriction of intramolecular motions. That is basically considered the important role of the vibrations. In this case, we are working in a region with big energy gaps. So non-radiative decay will go mainly for because the overlap of vibrational states. And the other case is the model called restricted access to the conical intersection, where we are working on systems that can explore regions of the potential energy surfaces of a very small energy gaps between the ground and the excited state. And in this case, the system, when it's in solution, can decay to the ground state because of the presence of these conical intersections, the regions of similar energies. And we try in the solid state or in the molecular crystal to block these conical intersections. So our group have been working in particular in the case of molecular crystals because they are extremely interesting and we can control and we can understand very clearly what is the three-dimensional structure of the system, and we can try to understand what is the effect of the three-dimensional structure on the non-radiative decay mechanism. So there are many challenges related to the computational description of excited states in organic crystals. First, we need to take into account that you will always have a competition between the localization of the excitation and the electron transport that you can have that is related to the localized nature of the excited states as well. And taking this into account, we can think about using either embedding methods where you consider a central region of your system where the interactions with the environment described are a lower level of theory, or we can try to describe the whole periodic system using periodic boundary condition methods. Now, the thing is like for organic crystals, we have like in most cases, the excited states are localized on a few molecular units. So the description of excited states is better it's better obtained if you use embedding methods. So another point that we should take into account is like when you form aggregates, depending on the orientation of the transition dipole moments. And here we are thinking about the Kasha-Exciton model. If we have like a orientation of the dipole moments related to H aggregates, basically if you have side-by-side orientation for the monomers, we will have like the emission from the S1 state in the dimer is supposed to be forbidden. So one assumption could be like if you are able to obtain a crystal where you have quite a lot of H aggregates, you should be able to switch off fluorescence, while if you have a crystal with a lot of J aggregates, in that case you will have like twice the emission from the S1 state, and consequently in that case you may have something like aggregation induced emission. When you think about this model, the Kasha model is a very an approximate model, and it doesn't it's not fulfilled all the time. But there is another thing, and it's like one of the main contributions to the quantum yield, as we think in the question that you used to calculate the quantum yield, is non-radiative decay. So for most of the systems, it's not enough to increase the radiative decay if you are not able to decrease non-radiative decay. I'm going to show you a few cases, and you can see later how you can what is the role of radiative versus non-radiative decays for some typical aggregation induced emission systems. So another issue here is, okay, how do we explore the potential energy surfaces? Because if we want to take a look at the whole potential energy surface and talk about the excited state mechanism, we need to be able to describe not only the regions with a large energy gaps that we can relatively do very well using TDD method, but also we want to be able to explore conical intersections. And normally TDD methods are not very good for describing this kind of these parts of the potential energy surfaces. So to do this kind of studies, we normally use a combination of single reference methods and multi-reference methods. We particularly like to work with the regions with big gaps to use CC2 and ADC2 methods. And we also, of course, use as well TDFT. And to calculate conical intersections and take a look at regions of very small energy gaps, we normally use multi-reference methods. And normally optimize conical intersections using CASA-CF methods and evaluate the energies with CASPT2 methods. So if we are working with the excited states of molecular crystal, normally the procedure that we use is to start for optimizing the crystal using periodic DFT. And after that, what we do is like we analyze the geometries of the system. Then we do an analysis of the exciton couplings in the system to have an idea of how important is the level of the localization of the excitation. And following that, we do excited state embedding calculations. This is a workflow that we follow very often. We put together a series of tools to calculate molecular excitations in molecular solids. And they were implemented by Miguel, one of my PhD students, and in the code from MASH. And we have a set of tools that are designed to analyze excited states in molecular crystals. One of the features of the code is that we add some embedding electrostatic methods to take into account the effect of the periodicity on the crystal on a central excited molecule. And all of these methods can be used to optimize a stable and stable minima and also conical intersections. So I invite you to take a look at the code if you are interested in this kind of problems. So as an example, I'm going to show one of the systems that we've been studying quite in detail, and it's the aggregation induced emission in some crystals that show intramolecular proton transfer. One feature of intramolecular proton transfer is like when we have this kind of molecules, we have like two forms that are in equilibrium. We have the enol form when you have the hydrogen on one of the electronegative atoms. In this case, is attached to an oxygen atom. And when you go to the excited state, then you have like the transfer of this proton to the other side. So you have equilibrium between the enol and keto form. And depending on the system, you will have like, depending on the environment, you are able to modify the possible emission of the system. And this is really sensitive to the media. We look at two series of chromophores here. We took a look at two hydroxy chalcone derivative and also to some similar compounds that are derivative of hydrophenylpropanone, which are very similar to hydrochalcones, but they don't have one of the phenyl groups. Why the interest on these systems? These systems have found applications in organic lasers. There are a lot of experimental data for them, and this experimental data is provided for the single crystals. So we have their three-dimensional structure, we have reliable data of the quantum yields, and we also have quite a lot of data, experimental data about these systems. So we have started trying to understand what these systems that are very similar in a structure show properties so different. For example, you can see for the HC series that there are a set of molecules that have like relatively high quantum yield, while we have like when you substitute, for example, this system with a methyl group or a methoxy group on the para position, you completely switch off fluorescence. What we see in the case of HP derivative is like, regardless of the substitution that you have, of the substitution pattern, you will have like these systems are highly emissive in all cases. So we try to explain the reason for the differences between this series of molecules, and our main focus was to explain the difference between HC1, HC5, and HP1, okay? So we started taking a look at the potential energy surfaces in the gas phase. And we found that for this kind of systems, as I explained before, when you have excited state proton transfer, you have competition between the relaxation between the enol or keto channels. We have that for both channels, you will have an accessible conical intersection related with the rotation around this dihedral angle here. This happens for all of these systems, and there are not very significant differences in the potential energy surfaces. Maybe the main thing between them is like in the case of number 5, that is the system that is not emissive in the solid state, we have like the excited state proton transfer process is extremely favorable. So we did adiabatic dynamic simulations using surface hopping, and what we observe if we analyze these two systems, HC1 and HC5, we have like, there is a distribution of the trajectories of the population of the enol and keto channels. And we see that that happens in the case of one, where the stabilities of the enol and the keto structures are relatively similar. But we have like for the case of 5, where the keto form is much stable, that most of the trajectories will stabilize on the proton transfer system. So this is the main mechanism in vacuum. What happens when we are talking about the molecular crystals? When we analyze the molecular crystals first, we took a look at the structure of the crystal and tried to figure it out. Where we have some particular motif, we were more likely in one kind of molecules or the other. And we saw that for the case of for the series AC, we have a large population of herringbone motif. However, in the case of the system that are not emissive in the solid state, that are HC4, HC5, and HC7, we have a significant amount of T-shaped motif. And these motifs are very common with the HP series. So we cannot really say anything conclusive just looking at the 3D dimensional structure. So to analyze the excited states in the molecular crystals, we did a series of calculations and tests. We use a mix of methods, and I'm going to show you the main conclusions that we obtain. I mean, if you have any particular question I can answer you later. So the first question that we wanted to answer was, okay, the difference between these systems is related to radiative decay or to non-radiative decay. We did an estimation of the radiative and non-radiative constants, and you can see like radiative decay for the rates for radiative decays are very similar for the three systems. So the main differences between them will come from the non-radiative decay. So we explore the potential surfaces using embedding methods, and what we found was like after the initial excitation, the system relaxes to the enol form. You have proton transfer in the excited state, then you have the keto form, and then in the keto form, the system, if we are talking about one, won't be able to reach the conical intersection. What do we get in terms of the geometries of this? If we compare the conical intersections that we get in the solid state and we get in vacuum, you will see like the conical intersections in the solid state are a little bit more rigid. I mean, the rotations are, of course, restricted in the solid, and you will have like the angles related, the dihedral angles are smaller. So if we compare the energies of the conical intersections for 1 and 5, we can see like in the case of 1, that is the system that is emissive, you will have like the conical intersection cannot be reached. While when we are talking about the system 5, that is the one that is not emissive, the conical intersection, while it's lower in energy than the one that we have in vacuum, is still accessible. Some general comments about this. I mean, we have like the reason for the stabilization of the conical intersection here is the electrostatic interactions with the environment. If we just switch off the electrostatic embedding and you were with mechanical embedding, the conical intersection for 5 is also not accessible. So the reason for the stabilization of the conical when you are in the solid is just the electrostatic interactions with the environment. So what happens for HP? In the case of HP, we can see that we have a similar behavior that we have for 1, and you will have like the conical intersection is not accessible in the crystal either. So that explains like the main differences between the systems, between the series, but it doesn't explain why HP series is more emissive than HC. And to analyze that, we took a look at the competition between proton transfer, exciton coupling, and we took a look at the differences that we have in reorganization energies between the enol and the keto forms. You can see like the reorganization energies for the keto forms are much larger than the reorganization energies for the enol form, basically because proton transfer is extremely likely for this system. So what happens is like when you have a system and when you have competition between enol formation and keto formation, if the keto formation is really likely, the system, the electronic density will localize on one of the units, and electron transfer is extremely unlikely. So this is what happens for HP1, and this is also what happens for HC5. While in the case of HC1, you have a competition between enol and keto form relaxation. And in this case, you may have some competition between formation of the keto form and the electron transfer between the systems. So if you want to achieve like a large emission in this kind of systems, you need first to make sure that the conical intersections that you have in your system are not accessible. But you also need to make sure that the proton transfer process is extremely likely, so you are able to stabilize the system once you are in the keto form, once you are in the excited state. These are the differences between the electronic density between HP1 and HC5. You can see that they're relatively similar. I mean, the main difference between them is that for this case, you have like the the conical intersection is accessible. So one last question to answer is, does this mechanism change if you consider or you take into account more molecules in the model? I mean, we have done tests with using like 2, 3, 4 molecules in the QM region. And because of the level of localization that you get of the electronic density in this instance, you could see that the energies converge once you have more than two molecules in the QM region. Consequently, I mean, the model is particularly stable, and we can use this to explain like the differences between the emissive response of this series of systems. So thank you very much for your attention. I think I took a few minutes, but okay. You can ask me any question later. I would like to acknowledge past and current members of my group, in particular Michael, Miguel, and Liliana. I mean, Michael and Miguel have done most of the work that I shown here. Miguel also had a tremendous role on the development of Fromage, and Liliana is also working on aggregation induced emission. I mean, other people who contributed to this are Amir, Guarda, and Matt, who were master students at the time. And I will also want to acknowledge Federico, who is a new postdoc in the group, and Luis Blancafort, who has been working with me quite a lot on revising some of the main models that I use in aggregation induced emission studies. So yeah, just to acknowledge as well Queen Mary, EPSRC, and Royal Society, Thomas Young Center, and also the Leverhulme Trust. Just a bit of advertisement here. We have a PhD position that is to work on understanding the effect of aggregation in light-emitting organic crystals, with focusing the role of triple states. The deadline for the application is in a few days. So if you know anyone who is interested, or you are interested yourself, please email me, okay? Okay, thank you very much. It's been a pleasure.
That's great, thank you, Rachel.
Good.
Stoyan has a question about structure mechanisms for you.
Yes.
So Stoyan, if you'd like to unmute yourself.
Yes.
Yes, thank you very much. It's fascinating to see some of these predictions that you have, both very nice novel phenomenon, very relatively recent, and that you can do this computationally at Queen Mary. So maybe some of the things that we could discuss at some other time when we are both at Queen Mary. But specifically, I was curious, how accurately can you predict some of these properties for the excited state structures or the different mechanisms? Because you mentioned, for example, you have radiative decay, non-radiative decay. Can you actually predict and compare with experiments the radiative decay for some molecule, and then some non-radiative decay, and that's how you figure out like what the mechanism is? Or I'm not too sure about the controls and the kind of prediction capability you have.
I mean, modeling excited states is quite challenging, and it's more challenging when we are talking about solid state, or when we are talking about condensed phase in general. So, I mean, we before starting any of these studies, the first thing that we do is to analyze the experimental data, and we compare emission and absorption data from the experiments. So that's the first thing that we do. And so we get more or less an idea of how good the methods are, at least to describe the stable points on the potential energy surfaces. So we tend to work with methods that are good to describe emission and absorption spectrum, and that show good agreement with experimental values of absorption and emission. And for the study of conical intersections, of course, it's difficult to, I mean, you don't have a way of checking if the structures are fine. But of course, here what we try to do is to use the approach of trying different methods. And we normally work to optimize conical intersections with CASSCF, and sometimes we need to even go further, because sometimes CAS-STF is not enough to give you a good structure for a conical intersection. So we need always to check if the energies that you get for the conical intersections with CAS-STF are similar to the ones that you get with CAS-PT2. And if not, I mean, for these cases, it's very difficult to optimize the conical intersections with PT2 because these systems are relatively big. But in some cases, what we have done is try to do some manual rotations of different coordinates to make sure that we are working in the right region of the potential energy surfaces if we work with PT2, for example. What you mentioned about the comparison with the experimental data, the rates, for example, the rates, you can get the rates from the experiments. And in the case that I showed, the radiative decay, you get it by integrating the emission spectrum. And you can do that from the experiments as well, but you can also get this data using time-resolved spectroscopy. And for one of the systems, for HC1, there are results of time-resolved spectroscopy for them. So our values are not like very good, that they are more or less on the order of the experiments. And so what we try to do is try to understand the atomistic mechanism and try to get as close as possible to what the experiments say, okay?